Okay. Hello, everyone, and welcome to July webinar of the London branch of the Institute of Corrosion, and thank you for joining. We're going to be waiting for a few more people because we had a lot of interest in this webinar, so we'll give others a couple of minutes to join. It's still 1 minute to go. Can someone confirm that you can hear me okay? Whether you want to
And
say it.
also me.
Yes, most importantly. If you want to say it in chat, type it that you can hear both myself and Henry okay.
Yes.
Perfect.
Thank you, Mohammed.
Thank you. So we're getting a couple more people. I'm just admitting everybody into the room.
Okay.
And we'll start very shortly. Okay, so it's 5 p.m. here in the UK, start of the webinar, and thank you all for dialing in. My name is Polina Zabelina, and I am current chair of the London branch of the Institute of Corrosion. And this is our second webinar of 2023. So welcome, everyone. And today we have an excellent presentation by one of our London branch committee members, Henry Leon. And I'll do a quick introduction for Henry. He has over 17 years of experience in petrochemical, steelmaking, and oil and gas industries. He's certified as NACE corrosion technician, NACE MR0175 certified user carbon steel, NACE senior internal corrosion technologist, and CP4 cathodic protection specialist. He started his career in Venezuela, and now he is in Netherlands, where he leads upstream asset integrity team at TACA Global. So we are very lucky to have Henry both on our committee and also at today's webinar. And without further ado, I hand over to you, Henry.
Thank you very much. Good afternoon for everyone. Welcome to this webinar. Thanks for joining us. Today, we will discuss about some field test and troubleshooting for cathodic protection. And this will be the content that we will see today. First, I will give you a couple of references about how to determine which surveys suits your needs. I will also make a reference to the field test pre-check. What do you need to do before you actually begin the survey? Also, I will explain a few basic concepts that they are important to understand the surveys that you can do to assess your CP system. And we will also check, or I will explain about a couple of non-intrusive pipeline survey techniques. For example, the structure-to-electrolyte potential, CIPS, DCVG, ACVG, PCM. I will also give one example of troubleshooting that I had with a CP system in the past. I will refer to a few applicable standards in general for CP assessment and field test. And finally, we will conclude with some information about the Institute of Corrosion, how to become a member, and what are the training opportunities that we offer. Okay, so sometimes you might come to the situation that you know that you need to take care of the integrity of your pipeline, but you don't know what to do. So one good starting point would be to check some standards that they are already available for us. One of them is the pipeline external corrosion direct assessment methodology, also known as ACDA. This is the AMPP SP 0502. Here you can see depending on what you're looking for, what's your interest, you can check if the survey it's applicable or not, if there are some conditions for it to be applied. Something that calls my attention when it's a rocky terrain. Key number 3 is you need to make sure that the operator that is carrying out the survey is qualified for doing this. So you need to have quite some experience. The conditions listed in this standard, they refer to coating holidays, anodic zones or bare pipe, when you are near a river or a water crossing, under frozen ground, straight current, etc. So with this standard, you can check if the close interval survey is an option for you, or ACVG, or the DCVG, or Pearson, or PCM. Another standard that is available for us is the NACE or AMPP SP0200 for steel-cased pipelines practices. Here we can also link different surveys with the possible scenario that we might have with that specific casing. So we can see here what are the possibilities, the short description of the method, some comments, limitations for the DCVG, AC current and attenuation, the A-frame that we will discuss this one in more detail later on, pipe to casing current attenuation, close interval survey or CIPS. This one we will also discuss in more detail. Pipe cable locator using a radio signal, internal resistance, electrical resistance, forward test, temporary intentional short. And so to make my point, at least when you don't know which survey you need to carry it out, at least you have these two standards to have an idea. But please always try to go to a specialist who could give you the proper indication and guidelines and guidance that you need to make sure that you are going to get the information that you need to assess the integrity of your asset. Okay, something that is also important, it's once you have decided which survey you're going to carry out, it's important to have an idea of some pre-checks that you have to do before doing the surveys. Some of them, they might sound like, yeah, of course, it's necessary, but sometimes it's not done beforehand, and you need to do it not, let's say, during the planning. Simple things like, okay, locate the pipeline and identify the pipeline, because most of these surveys, you want to be on top of the pipeline. So if you are in the middle of a residential area, it might be complicated to follow the pipeline. So for sure, that's the first step, very important. Locate the pipeline and identify its location above ground. You also want to have an idea on how will be the right of way. Is it well maintained? Are you going through residential area, commercial area? It's in the middle of the jungle. Are you going to cross a river? All these kind of things, you need to be completely sure and of the what's the situation, so you can prepare your survey in a good way and avoid delays because of having to deal with surprises like high vegetation. Also, seasoning. In countries where we have different seasons, you need to take care that into consideration, that maybe During the rainy season, it's not possible to do the survey, or the other way around. You might be interested in doing it during the uh, rainy season. You need to think about it. And so you also need to try to get as much information about the pipeline. What's the pipe data? What was the design code, the size, the age, the type of coating? To give you one reference, why do you need to know about the type of coating? It's not the same setup that you are going to use in some equipment if you have a bitumen coating or 3 layers coating. So that's why you need to have this information beforehand. You also need to know about the soil resistivity, because as I said, you might be interested in doing the survey maybe during the rainy season, during the dry season, or during the summer instead of during the winter. You also you should try to get as much information as possible about the rectifiers that are in the system, in case that the pipeline that you are going to assess has CP. Because for some surveys, it is important to synchronize the rectifier and make sure that they are all switching off at the same time for the surveys. You also want to know if there are galvanic anodes in the line, because if you are not aware of these ground beds, you might think that there is a coating defect in the pipeline. You might order to excavate that area, and then you will find out that those are galvanic anodes. You also want to have construction history about the pipeline. Do we have tie-ins? Do we have modifications? Do we have branches? Of course, this is important to avoid having to troubleshoot or having to have discussions with a pipeline owner to discuss about a strange result during the survey. And that's why also past surveys can be quite useful, because if they have already identified in the past challenging areas of the pipeline, then you might avoid some headaches and prepare yourself for the next survey. And as simple as it might sound, bring with you spare parts. For example, extra batteries for those equipment that operate with batteries, or extra cables for your equipment to connect to the stations. That might save you a couple of hours or days. Now, I want to explain these basic concepts, because if we don't understand these, it might be more challenging to understand the principle of the surveys that we want to execute. Okay, so, oh, 1 second. Okay. Okay. Can you please confirm that you can see that you still can see my screen?
Yes, we can.
Perfect.
Yes.
Thanks. Okay. The basics of steel making. Corrosion is a nature reverse nature, in the sense that, for example, to make a steel pipeline, what we have as a raw material is iron ore. Okay, it goes to a blast furnace, then oxygen converter, then to a pipe mill, and finally we have the steel pipe. Then when we place the pipeline in the soil or in the water, it will corrode if we don't take the proper measures. It will corrode and it will go back to iron oxide. That is from the chemical point of view, it's the same as iron ore. So basically, what we do in this process, especially in the blast furnace, we are injecting a lot of energy to the steel to transform iron ore into steel. So basically, in fact, from iron ore, we convert it into liquid iron, and eventually in the oxygen converter, we make steel. So that amount of energy that we are injecting in this step, it wants to be released, and it wants to go to the state that is in nature, and that's why steel structures, they want to go back to iron oxide. That's the status, or that's how they are in nature. And of course, those the pipelines, they are not uniform. Their structures, in their structure, they have cathode and anodes, and they have different behavior within one piece of pipe, and that's why in a steel structure we have a corrosion cell. Once we place it in the ground or in the water, you will complete the corrosion cell, because we will have a conductive electrolyte. That would be the water in the soil, or the water in the seabed, for example. We have a metallic path, that is the pipeline, and we have a cathode and an anode. So the scenario is given for corrosion to take place. So what we want to do with cathodic protection is to avoid those differences in these micro cells that we have within the steel structure. If if we avoid the difference between the parts, the micro anodic and micro cathodic parts in the steel structure, we are not going to have corrosion, because basically there is not going to be any driving force for the chemical reactions to take place. So that's why we want to polarize the structure. And when we have usually when we have piece of steel in the soil, we might have a natural potential of minus 500 millivolts versus copper sulfide electrode, and then we want to polarize it up to minus 700, or later on in the next slide, we will see that minus 850 millivolts is the good target. So what do we do with cathodic protection? Basically, when we use, for example, aluminum anodes connected to a steel structure, as you can see here, aluminum, it's more electronegative, more active than steel. So it will tend to provide electrons to the steel, and then the polarization of the steel will take place, and we will do this. Then, how do we know how far do we want to go? Uh, when we use the Purvex diagram to correlate the potential and the pH of the steel, we can identify at least three areas. Two where we have active corrosion, one where we have immunity, and the one where we have passivation. So when we come into this situation, immunity, this is the result of applying cathodic protection, because we're dropping the natural potential of the structure up to minus 850 millivolts versus copper sulfate. In this area, we have immunity. It means that we have almost zero corrosion rate. And that will happen in a acidic up to neutral pH environment. This is where the cathodic protection criteria are coming from. And talking about the cathodic protection criteria, basically we have two of them. The first one is the IR a drop-free potential of a minus 850 millivolts versus copper sulfate electrode. Because a steel structure is considered to be protected when it has a structure to electrolyte, could be water, could be soil, and a structure to electrolyte potential of at least minus 850 millivolts or more negative, meaning that it could be minus 950, minus 1 volt, but it has to be at least minus 850. With this criterion is based in the fact that we can eliminate the IR drop from the equation, and this can be done by switching off the TR or the disconnecting the galvanic anodes or placing the electrode close to the structure. Okay, and it's important to bear in mind that once we switch off the TR or we disconnect the anodes, we will have a peak in the potential reading. It will become more electronegative, then more electropositive, and eventually depolarization will start taking place. So we have to know when we want to take the reading, and usually it's less than 1 second after we switch the TR. We need to take the reading. To do this, and this is related already to the CIPS survey, where we need to define a on-off rate. Usually you do this by interrupting the TR with a rate of, let's say, 1 second off and 3 seconds on, especially to avoid depolarization. The exact timing will depend on the characteristics of your pipeline, the coating, the soil, or the electrolyte. It could be something like 0.5 to 3 seconds, the off time, and then the on time, something like 1.5 to 9 seconds. Again, the quicker your pipeline depolarized, then the shorter the the cycle. And the longer it takes to depolarize, then you need more time to be able to have a correct reading of this peak. And we also have a second criteria, that is the 100 millivolts cathodic potential shift. And so it's also considered that an extractor is protected when there is a minimum of 100 millivolts of cathodic protection of cathodic polarization between the structure and the reference electrode. And in this criteria is used, for example, to the tank's bottom, where it might be challenging to reach minus 850 millivolts. The 100 millivolts could be easier to achieve. Okay. Okay. Now we're going to discuss some non-intrusive surveys, in the sense that we don't have to touch the pipeline, either from the outside or from the inside. One example of the inside or assessment from the inside would be ILI or smart pigging. These surveys are non-intrusive. The first one that we're going to briefly discuss is the structure-to-electrolyte potential. We can use this technique for different purposes. It's the simplest that we can have, and it's already giving us a lot of information about our CPE system. So first, it helps us to confirm if our CP system is following the criteria or the criterion that we choose. We can also this one to check electrical isolation, the continuity of a structure when we have issues with a road or a railroad casing, shielding effect, stray current, or a coating evaluation. It's important to bear in mind that when we are executing this survey, we need to make sure that we report the eye drop free potential. For example, if we are on the field and we place the reference electrode and we touch the pipeline by means of a test station or a valve, we might have a reading of minus 1030 millivolts against copper sulfate. And if that technician it's not aware that we might have IR drop, we could say, we're in compliance, we're okay, because we need at least 850 and we have 1030. But in fact, we need to make sure that we are able to identify what's the IR drop, because if, for example, we could have 30 or 300 millivolts as IR drop, then when we do the correction, we will realize that we are not in compliance. Then the second survey that we can use is the closed interval potential survey, or CIPS. This one is a continuous potential measurement method. We used to have a measurement every 1 or 3 meters. Usually we choose a gap between the readings according to the depth of the pipeline. We need to use wires and data loggers, of course, to record the readings. It's used to check the CP protection level along the pipeline. We need to synchronize the tiers. And as I said, we usually set the interrupter in a rate of 4:1, meaning that we have the off period should be at least 3 seconds to avoid depolarization. Okay, so as I mentioned for the in a previous slide, if we have chosen 0.5 seconds off, then we will need to keep the TR on at least 2 seconds. With this survey, what we do is that we connect if we have TP, okay, we could use the rectifier. If not, if we have galvanic anodes, then we need to use an external power supply, battery, for example, and we need to use also an interrupter, okay, because we need to make sure that we know how much current we are injecting, and we need to make sure that we are switching as we need in a controlled way, using the cycle that we need to use. So we connect to the test station. We use we set up the interrupter and the rectifier. We make sure that we have a GPS synchronization with the CIPS equipment, and then we walk along the line to record the readings. So we're going to record a potential, as I said, every 1 to 3 meters, and usually it goes by the hand with the depth of the pipeline. This survey is used especially to give us information about the health of our CP system. We are going to be able to identify areas where the CP it's not working properly, maybe because we have coating defects, or we have crossings with other pipelines, or a metallic contact with another structure. It's quite simple, and it gives a lot of information. It might help us to identify coating defects, but it's not the target of this survey. The main target is to say something about the CP system. Once we see an area where the CP is not in compliance with the criterion that we have chosen, then we will have to investigate in more details, and we might have to combine this survey with another one, for example, DCVG. Okay. So DCVG is a direct current voltage gradient. This one helps us to have an accurate detection of the defects in the pipe coating. The target of the DCVG is not to say anything about cathodic protection, but cathodic protection and coating is a perfect marriage. So we need to make sure that both are okay. If we want to have a CP system working properly, our coating system should be also working properly, should be in good shape. So that's why DCVG is so important to assess CP. It allows us to have an evaluation of the size of the defect, the length of the defect. That's also important, because if we're doing the CIPS, as I said, we will know that in one area we have a problem, but it could be a problem that is 1 meter long, 5 centimeters long, 12 meters long. And the CIPS doesn't give information about how long the defect is, but the DCVG does. And we can also have an evaluation of the current state of the corrosion in the steel that is exposed, because the DCVG can, and we will discuss that in more details in a few minutes. It can give us information about, okay, we have a defect, but is the CP capable of protecting the exposed steel in this scenario? We will hear more about it in a second. We can also confirm the location of galvanic anodes, and we can investigate areas of possible electrical interference. And in this case, with the setup for interrupting the TR, if we have CP, is different. We set the cycle very fast to have a on period less than the off period, meaning that it could be, for example, 1/3 of a second on and 2/3 of a second off. Okay, a briefly explanation about what's the DCVG. First, we use a voltmeter that can flick to the right or to the left, and we can have an indication of how many millivolts we have. They are quite accurate. We can have a reading up to 1 millivolt, and we will see in a minute why that's important. One of the specific characteristics of this type of equipment is that it will flick to the right when it's a positive reading, and to the left when it's a negative reading. Usually multimeters or voltmeters, usually they go only in one direction. But for this survey, it is important to know where the current is going to. So this survey is done in the following way. If we have the CP, or if we are using an external power supply, we need to have an interrupter that is connected to GPS and is connected to our equipment, for the DCVG equipment. And so we also need to have the readings between two known locations to have the reference of what's going on between that area. That's why you see here two different signal strength, and we need to know the distance between these two locations. This could be, for example, two test stations. So the first step is that you walk in parallel. Both reference electrodes, they are moved in parallel to the pipeline, as shown in this picture. And once you're getting closer to the defect, you will see a that the dial is moving. Then when you are coming on top of the defect, you are not going to see any movement. And then when you are passing by, the dial will move in the opposite direction. Then you in that situation, you have identified a location of a defect. Then the next step is, once you have identified a location or a defect location, you need to move perpendicular to the pipeline to determine the remote earth potential. That is also known as the over the line pipe to remote earth voltage. So you will do several readings until you come to the point that you have 1 millivolt or 0 millivolt difference. These readings, you are going to do it, each one of them, approximately 1 meter in between, 1 meter, 1.5. Okay. Once you have a 1 millivolt reading, that's your that's when you stop. And depending on how much detail you want to get about that defect, you can rotate along the pipeline, and you can determine if the defect is on top of the pipeline, at the bottom, left, right. So depending on how much time you are willing to invest, you can get more and more details. One of the advantages of this survey is that you can get quantification of the damage, of the defects in the coating. So you can say, okay, all those defects that they are around 36 and 100% IR, sorry, they are quite large, and usually they need to be taken care of, in the sense that you want to excavate and repair them. Those that are between 16 and 35%, they are moderate, and they might be okay depending on the remaining lifetime of your CP. And some companies, they might accept it. Maybe the pipeline is going to be out of service in a couple of years. And those that are that they have low criticality, between 0 and 15% of IR, they might be left, and the CP will take care of it. It's important to mention that these values, they are, let's say, just a reference. It's we can't correlate IR percentage with a specific area. It's not like each by every 5 or 10% IR, we can say it is equivalent to 1 or 2 or 10 square centimeters of exposed area. It's not like that. It's also important to mention that we need to consider if in if in around this pipeline we could have development of calcareous layers because of the CP. Remember that if we have the high pH and we have the chemical composition required for this, the CP will tend to develop a calcareous layer in the exposed steel. And then we will see that as an defect that is smaller than expected, because we will see a high IR percentage, but in reality, once we excavate, it's going to be smaller. And on the other hand, when we have a acidic soil and we don't have the conditions to develop calcareous material, we might have a IR reading that might give the feeling that we have a small damage, but in reality, once we excavate, we will realize that they might be larger than expected. Okay, I also mentioned that with DCVG, we can have an idea of the defect type. So we can say if we have a cathodic anodic defect, and this is when the rectifier is on, the cathodic protection is efficient, so it is protected. But when the rectifier is off, the cathodic protection is totally deficient, so the pipeline doesn't polarize, it's going to corrode. Then we have a cathodic scenario that if the CP is on, the pipeline or that defect is protected. And also, if we switch off the CP system for a few hours or days, the coating keeps the polarization in the pipeline, and that specific defect is going to be protected for a couple of hours or days. And the worst case scenario is when we have a defect that is anodic. So even if the CP is on or off, it's going to be corroding. Usually, despite the size of the defect, all those classified as anodic should be repaired, even if they are small. And this is one example of how you can record your findings. Okay, the PCM or a pipeline current mapper, we don't need to have a contact to the soil. The equipment, we place it just to have an stable reading, but basically the equipment doesn't have to be touching the ground because it's an electromagnetic field principle, so that's quite advantageous. With this one, we can characterize the current flow in a pipeline. It can be used at road crossings, identify the contact between pipes. We can do 3D pipeline tracing in the sense that this one allows us to get information about how deep is the pipeline. This is quite useful in pipeline corridors where we might have 2 or 3 pipelines crossing each other, and maybe we have a 2D plot and we don't know which one is on top of the other. With the PCM, we can have information about how deep each one of the pipelines are. We can measure the current attenuation along the pipeline, and we can indicate pipe anomalies like coating defects or metal contact with other structures, etc. Okay. Okay, so on the left hand side picture, we see a normal current distribution. We have here a transmitter that is part of the equipment. Let me find that. Let me explain a little bit about the principle of this survey. We have a transmitter that is connected to the pipeline, maybe through a test station or a temporary connection to ground. But we need to have a physical contact with the pipeline. So this is the transmitter, and we have a receiver that is the one that is going to give us information about how deep is the pipeline and what's the current received in a specific part when we are on top of the pipeline. Okay, so our pipeline is connected to the transmitter, and then with the receiver, we're walking through the line and doing the readings. So this is a normal step-by-step procedure, and depending on the distance that you have between readings, you will have a higher or lower current readings. The important thing to have into consideration is that it should be uniform. Let's say if we have, in this example, 100 milliamperes difference, I would expect that the distance between each one of these locations would be quite similar. Because if it's not the case that we have a large change in the current distribution, we might have an anomaly or a contact with another metallic structure. And then we need to identify this defect. And to do that, we will discuss about it with the ACVG application that we have with the PCM equipment. I also want to mention one thing, that the PCM can be quite useful when we are in the middle of a road crossing, because it can help us to avoid the necessity, for example, drilling holes in the asphalt. This could be a preliminary test. We can check upstream and downstream the road cross, or if we have a canal or a river, we could check on both sides. And if we have a uniform current distribution, we don't need to assess in detail, for example, doing a CIPS in between those locations. We can skip that. We can say, okay, coating is okay. We are not losing a current. We can move on. That could save also some time. Okay. Now, ACVG is the last field survey that we're going to discuss today, and is the oldest one that has been used to assess the coating in our system. The principle is that you have a transmitter that is connected to the pipeline, and you have boots, and those boots are connected between the two operators, and they are also connected to the receiver that is carried by one of the uh, surveyors. So the principle here is that when you have a defect, okay, like here, when you are far away from it, you have a low signal. It's you hear a sound, and it's just a beep. Once you are getting closer to it, it will be a little bit higher. And once the first surveyor is on top of the defect, you will have again you will have the high signal. Then he will move away, and then the defect will be in between the two inspectors. At that moment, you will have a low signal. Later on, the second surveyor will pass by on top of the defect, and you will have again a high signal. That's where you are going to have these two peaks, and in between those two peaks, you have identified the location of your defect. One of the big difference between ACVG and DCVG is that ACVG is not capable of telling us how large the defect is, and we are not capable of getting any information about the location or the length of the geometry of the defect. But okay, we get information about what it is. So nowadays, the Pearson method might be used like this, but the same principle can be done with an extra um, piece of equipment that comes with the PCM equipment, and it's called the A-frame. The A-frame will give a similar scenario to the one created between the two inspectors. So instead of walking along the line, you don't have to do that, because when you use the PCM, you can combine both techniques during the survey. You can use the PCM to check, let's say, every 1 kilometer, you're going to do a reading. If everything is okay, you move on. Once you identify a defect or a one point where the current is draining, you need to use your A-frame and try to pinpoint the location of the defect. And in some cases, you might have to do a couple of PCM readings in between, and finally you will be able to do this. And it might sound complicated, but it's way easier and quicker than doing the survey along the whole pipeline, especially when it's a long pipeline, maybe a new one, good condition, that you just want to go through very quickly. Okay, finally, I will share one experience about CP. At the beginning, I told you that sometimes, yeah, there are things that they seem to be uh, uh, obvious that you have to take care of it, but things happen and you have to double check everything. A few years ago, I received a piece of a pipeline to perform a root cause analysis. The defect looked like this. And then I said, oh, it looks like a straight current. Maybe we don't need to do a full root case investigation. But I said, okay, let's go there. So when I went there, I did electrolyte to structure readings, and I realized that the polarity was positive instead of negative. And then I said, okay,